So next we need to understand the concept of Avogadros number before we can come to the ideal gas. It's just a number. It's this exact number, 6.02 times 10 to the power 23. So many of anything. So you need to say so many of what? So many items make 1 mole. Okay, so if I have particles, I'm going to say 6.02 times 10 to the power 3 particles is 1 mole of particles. If I have so many pencils, I'm going to say I have 1 mole of pencils. So you just need to count up the number of items. So that's defined as my Avogadro number. Okay, it's sort of not an integer number, so you may think that why have we taken such an odd number to define Avogadro's number? And that's because there are that many particles in 12 grams of carbon. It contains exactly 1 Avogadro number of atoms. Okay, so we can take this 12 grams. This is the molar mass, yeah, and we're going to divide it by the number of atoms, n. Avogadro's number, Na. If you divide the molar mass of a substance by the number Na, which is the 6.02 times 10 to the power 23, you will get the mass of the atom, the atomic mass. Yeah. So N equals mass divided by molar mass. Then that little n represents the number of moles. But mass could be any mass that's given to you. Say the 12 grams of carbon that was given to you. Okay. So 1 mole is the amount of substance that contains as many particles as they are in 12 grams of carbon 12. Its unit is mole. It's written as MOL. Sometimes can be written MOLE, but in short, it could be written MOL. The type of substance may be an atom or a molecule and needs to be specified. So if you have 6.02 times 10 to the power 23 molecules of oxygen, then you have 1 mole of oxygen molecules. Yeah? If you just have 6.02 times 10 to the power 23 atoms of oxygen, then you have to say you have 1 mole of oxygen atoms. So it's important to specify 1 mole of what. Here's the ideal gas law now. We are in a position to understand all parts of this law. It simply says PV equals nRT, where P is the pressure of the gas. So we understand the pressure of the gas and what it depends on. V is the volume of the gas. Okay. N is the number of moles. Now we understand that. R is something called universal gas constant, and I'll come back to that in a minute. T is the temperature in Kelvin. So T needs to be, all of this needs to be in MKS units. And certainly T needs to be in Kelvin. So coming back to the R, it's called the universal gas constant or molar gas constant. And it can be expressed in one of 2 ways. One way is R equals 8.31 joules per mole Kelvin. And this would be our MKS way of expressing it, or SI. But you often will find it expressed in this way. R equals 0.0821 liter atmosphere per mole Kelvin. Okay. This is not the SI unit, but your problem might give you R like this, or R might be just a constant given somewhere else, not with the problem. So what I suggest you do is you convert all other quantities like pressure, volume, N and T to match the units in which the R is given to you. So if R is not given in MKS units, then make sure, if it's given like this, then make sure you have the volume measured in liters, pressures and atmosphere, yeah, and so on. The lower part is identical. So you're always, N is always in moles, T is always in Kelvin. This here is not a typo. This digit changes between 3 and 2. This is not a typo. This is exactly how it is. Okay, it's meant to be like this. Okay, so this is called my ideal gas law, PV equals nRT. Yeah, you can use this to study gases, real gases, at standard temperature and pressure, or if their temperature is higher than that and their pressure is lower. Yeah, then we say that the ideal gas law applies quite well to real gases. Another way of expressing the ideal gas law is PV equals N, this is now an uppercase N, KBT. Okay, where N is the number of molecules. It's not the number of moles, it's the number of particles, right? So you need to multiply by Avogadros number, yeah? So N equals little n times Avogadros number. Kb is called the Boltzmann constant, and Kb is simply R divided by Avogadros number, and it's this value here. So one or the other will be given to you. Either R will be given to you or Kb will be given to you. You can always convert between the two using this. If you just compare this expression with PV equals nRT, you will see that nR and uppercase NKB must be equal to each other. The left-hand side here represents large scale. We're talking about moles, which is large number of particles, yeah, and the universal gas constant. This side, so that's macroscopic or large scale. And this side represents the microscopic or small scale. Now we're talking about individual particles, and we have the Boltzmann constant, okay? So this is called the microscopic. So this expression relates what happens on the large scale to what happens on the small scale. Which one of these two expressions you use depends a little bit on the question, what you're being asked for. If you ask for number of particles, it's best to use the microscopic because this contains number of particles. If you're asked to find, say, number of moles, you're going to use the other expression because you need the smaller lowercase n. So it's important to keep the distinction between lower and uppercase n in mind and not use them interchangeably. So let's do a simple problem on this. Calculate the number of moles in a 2-liter volume of air in the lungs of an average person. So here are the lungs, they are 2 liters. Note that the air is at 37 degrees Celsius, which is body temperature. Okay, so we are given this value of R. We're going to use PV equals nRT. So let me just change the color here. Let's write the ideal gas law. We're going to use PV equals nRT. And what are we asked for? We asked for the number of moles, which is this value here. We need to solve for n. So we have n equals PV divided by RT. I'm going to look at my units, and it's harder to convert R because there are many terms in the units here. So I'm going to convert everything else into these units. So my pressure needs to be in atmospheres. And we know that the lungs are at 1 atmosphere pressure, right? So we already have 1 for that. What about the volume? It needs to be in liters. And they told me it's 2 liters. So 1 multiplied by 2. Okay, maybe the decimal is not so visible. So let me put them in parentheses. Divided by this value of R. It's going to take me a while to write it. Times T. The temperature needs to be in Kelvin. I have 37, so I need to add the 273, right? 0.15. Sometimes we leave out the 0.15, just depends on the number of significant figures you need. I'm going to write it in here for now. Okay, you need to put all that in your calculator, and you should be able to get your answer and check against mine. So you should get 0.0786 moles. Yeah? If you want the exact number of particles, you're going to multiply this number by Avogadros number. Right? So it's still going to be a very large number, something like 10 to the power 22 or 21 you're going to get. Yeah? Let's do another problem. Large helium-filled balloons are used to lift scientific equipment to high altitudes. What is the pressure inside such a balloon if it starts out at sea level with a temperature of 10 degrees Celsius and rises to an altitude where its volume is 20 times the original volume and its temperature is minus 50 degrees Celsius? Okay, so clearly we need to make a sketch. Let me go to a different color. So we're starting the balloon out here. What do we know here? This is the ground at sea level. That means I have 1 atmosphere pressure, right? At sea level. What is the temperature? 10 Celsius, so that's 273 plus 10 to 83.15 Kelvin. And we have some volume V, yeah? Now the balloon rises up from here, and let's take this as its highest point where it is at. We don't know the second pressure, we need to find the pressure here. We know its temperature is minus 50 degrees, so we have 273.15 minus 50, sorry, beg your pardon, I could do that. So that digit is going to be a 223.15 Kelvin, yeah? And the new volume is 20 times the original volume. So let me write that as 20. Okay, at both points you can apply the gas equation, yeah? Which means I have PV equals nRT at my first position. Let me call all of these 1, yeah? And then at the second position, I can also write P2, V2 equals nRT2. Or I can see if I solve these for nR, each of these, then PV over T for one must be equal to PV over T for the other. So I can write P1, V1 over T1. I'm just solving for nR here. It must be equal to, when if I solve this for nR, that's P2, V2 over T2. And just to be consistent, all the 1 values apply here. So let me call this V1. All the 2 values apply to my second position. So let me call this P2. And this is in terms of V1. Yeah? And now you can just substitute in the values from here. You want to solve for P2. And you should be able to do that. And obtain your results. You should get P2 as 3.9 times 10 to the minus 2 atmospheres.